So this is a continuation of our 3.4 lesson. Our topic is linear programming. So we got an introduction to this in class on block day, looking at the taco and burrito problem. If you have not already looked at that, go to my website and check the class notes, and there should be enough information just written. It's not a video, but there's a lot of information written on the notes that will kind of help to explain the process for what we did. So that's the introduction. Today we're going to continue to look at a few other linear programming problems. So let's read our new situation. So Roma tomato plants cost $2 each. They are guaranteed to yield 8 pounds of tomatoes per plant. Cherry tomato plants cost $3 each. They are guaranteed to yield 10 pounds of tomatoes per plant. You want to spend no more than $42 for at most 15 tomato plants. How many of each type should you buy to maximize the pounds of tomatoes you'll get? So we're going to start by assigning our variables. You can use X and Y for your variables. Sometimes what I do is I choose letters that remind me of what they represent. And so I'm actually going to use R to represent the number of Roma tomato plants. I'm going to use C to represent the number of cherry tomato plants. And then one other variable that we'll be using in the objective function has to do with what we're trying to maximize, which is the total number of pounds of the total number of pounds of tomatoes. So I'm going to have P represent the number of pounds. All right, so next we have some constraints in our problem, and we're always going to write constraints as inequality statements. Inequalities involving our variables and involving some of the numbers looking at the information in the problem. So one of our constraints is that we can spend no more than $42. So we're going to use the fact that Roma plants are $2 each, cherry tomato plants are $3 each, and we can write that as an inequality, $2 times the number of Roma plants plus $3 times the number of cherry plants must be less than or equal to $42. All right, another constraint is that we can have at most 15 tomato plants. So the total number of Roma plus the total number of cherry must be less than or equal to 15. So those are the only two obvious constraints that are given to us in the problem. There are two other constraints that I will have you add in. These ones are implied constraints, and that is that the number of Roma tomato plants and the number of cherry tomato plants must be greater than or equal to 0. It doesn't make sense to have a negative number of tomato plants, so we'll add those in when it makes sense. All right, the objective function. So remember, the objective function is going to be an equation, and it has to do with our goal or our objective. In this case, it's to maximize the number of pounds. So we're going to have P for pounds represent 8 pounds times the number of Roma plants plus 10 pounds times the number of cherry plants. So that's our setup. Our next step is to graph and shade the constraint inequalities. We are going to set this up as a system of inequalities, and we're going to shade where the shading overlaps. Now notice how there's not a lot of detail given to you on the grid. It's just an XY axis. You can draw that on your own. You don't even need to do this on graph paper. But if we're using different letter variables, different letters other than X and Y, we need to label which is which. So I would recommend just keeping consistent. So the first thing they mention, R, let's just put that on the X-axis. The second variable they mention, in this case C, let's put that on the Y-axis. All right, so I just recopied over the inequalities so that I can see them here on mine. So looking at our first inequality, the R and C are together on the same side. I would recommend doing the intercept method. So if you're going to think about covering up R, when R is equal to 0, that's going to be the C intercept. So think about 3C equals 42. Divide both sides by 3, and you get C equals 14. And because it's just a sketch of a graph, just pick a point and label it 14. Let's go over here and do the R-intercept. So the R-intercept is when C is 0. So think about covering that one up. Think about 2R equals 42. divide both sides by 2, and you get r equals 21. So that's the r-intercept, and you want to make sure that you connect them right away. So don't think about doing any other intercepts until you connect those two. Let's look at, actually, before we do the next inequality, let's think about where we will shade. If we think about the test point of 0, 0, which is down here, if you plug in 0 for r and 0 for c, you get 0 less than or equal to 42. And that's true. 0 is less than 42. So we're just going to put in those teeny tiny shading arrows pointing toward the direction. We are going to shade toward 0, 0 because 0, 0 made the inequality true, and we always want to shade toward the solutions. Let's look at our next inequality. If you cover up r, the c-intercept is 15. Cover up c to get the r-intercept is also 15. So going back over here to our graph, we're just going to make 15 above the 14. It's going to be a little bit less than the 21. And go ahead and connect those. Now when we think about the shading this time, we do our test point of 0, 0. We get 0 less than or equal to 15, which is also true. So this one is also shading below the line toward 0, 0. All right, for the last two, for r values greater than or equal to 0, that's going to be shading above the r axis. For c values greater than or equal to 0, that's going to be shading to the right of the c axis. So we should see here that the shaded region makes this looking shape right here. I'm highlighting mine, but you can just shade yours in with your pencil. The shaded region is also called the feasible region, and the feasible region contains all of the points that represent combinations of Roma plants and cherry plants that meet all of the constraints. Next, we're going to look at the corner points of the shaded region, and we also call these the vertex points, and we're going to list them out. Before we list them out, above where it says vertex, let's write, instead of x comma y, keeping it consistent with how we labeled, let's write r comma c. So we want to make sure that we're putting the right number in the right spot. The first vertex point down here, 0, 0, is easy to get. So that'd be 0 Roma plants, 0 cherry plants. That would certainly meet our constraints because the total is less than 15. The price would definitely be less than 42. The next one up here, this one is easy to get because it's an intercept. So this represents 0 Roma plants, but 14 cherry plants. So 0, 14. This third point down here is easy to get. Another intercept. It represents the combination of 15 Roma plants and 0 cherry plants. Now the one that we need to do a little bit of work to find is this one. This is the intersection point of the two boundary lines from our system of inequalities. And so if we turn those into equations, 2r plus 3c equals 42 and r plus c equals 15, remember that when you solve a system of equations, you get the point of intersection. So when you solve the system, you can solve using substitution or elimination. I'm going to do elimination. So I'm going to multiply everything in the second equation by -2. You could have multiplied everything by -3, or you could have just done substitution. All right, so I don't get confused, I'm going to highlight the two equations that I'm adding together. So the first original equation, the new version of the second equation. So 2r plus -2r cancels out. 3c minus 2c is 1c. 42 minus 30 is 12. So that means it's going to be 12 cherry plants. So that's like the y value of our vertex point. Knowing that the total has to add up to 15, 15 take away 12 will leave us with 3 Roma plants. So once we have our vertex equations there, we're going to plug them into our objective function, which is telling us about the number of pounds. We want the maximum number of pounds. So let's actually rewrite that. The number of pounds is equal to 8 pounds per Roma plant and 10 pounds per cherry plant. So if we were to plug in our numbers, hold on. Let me redo that. So 8 times 0 plus 10 times 0. So it could be 0 pounds. Another option, 8 times 0 plus 10 times 14. Yeah, sorry, I messed that up. So the 8 is always going to be in front of the first substitution. The 10 is always in front of the second. The numbers in parentheses here, that matches up with the two numbers of our vertex. All right, so 10 times 14. So that option is going to give us 140 pounds, which is certainly better than 0. But let's see what the other combinations give. The next one, we have 8 times 15 plus 10 times 0. And that ends up being, so let's think about this, 8 times 10 is 80, 8 times 5 is 40, 80 and 40 is going to be 120. All right, and then let's check our last combination. So we're going to do 8 times 3 plus 10 times 12. So 8 times 3 is going to be 24, 10 times 12 is 120. Add those two together and we get our maximum number of pounds, which is 144 pounds. So the point that maximized the number of pounds was the point 312. So what I like to do is circle that in my table, but then what I'd like you guys to do is write out your answer in words. So we're going to write 3 Roma plants, 12 cherry tomato plants, for a maximum of 144 pounds. Okay, so to do a quick summary, to recap what we've done, the steps that we want to follow are assigning our variables, writing our constraint inequalities, write the objective function, which is an equation. We're going to graph and shade our constraint inequalities, see where the shading overlaps. We're going to list out the coordinates of each vertex point. We're going to solve a system of equations to find the intersection point, which will be our last vertex here. And then we take the combinations from our vertex points, plug them into our objective function to get the total number of pounds. What I'd like to do now is just talk to you about the setup of the next problem. So each one of these situations is a little different. So let's read through this. Better Books orders at least 100 copies per week of the current best-selling fiction book. It costs $2 to ship each book from the East Coast supplier, $4 to ship the book from the West Coast supplier. They can spend no more than $320 per week for shipping. It takes 5 days for shipments from the East Coast to arrive, but only 2 days for shipments from the West Coast to arrive. How many books should they order from each supplier in order to minimize shipping time? So that's one change in this problem, is that we're looking for a minimum instead of a maximum. All right, to assign our variables, we are trying to figure out how many books we want from the East Coast supplier. So let's let E represent the number of books from the East Coast, and then how many books from the West Coast supplier. So W, hold on. So let's have W represent the number of books from the West Coast. All right, so the way we set up our constraints are going to look a little different for this problem. So one of our constraints is that they order at least 100 books per week. So that means the number of books from the East Coast plus the number of books from the West Coast has got to be greater than or equal to 100. Another constraint is that they can spend no more than $320 per week. It costs them $2 to ship a book from the East Coast supplier. It costs them $4 to ship a book from the West Coast supplier. So that total shipping cost has to be less than or equal to $320. All right, for the objective function, so we're wanting to minimize shipping time. So let's actually have another variable, maybe S, to represent the shipping time, and that would be in days. So for the objective function, we can say the shipping time will be equal to 5 days for each book from the East Coast, 2 days for each book from the West Coast. And we're wanting to find the minimum this time instead of the maximum. Okay, So to graph and shade our constraint inequalities. All right, so I just copied over our inequalities here. So let's go ahead and first label, let's do East Coast books on the x-axis, W on the y-axis. And let's think about getting our intercepts. So let's look at the first inequality, cover up E. The W-intercept is 100. The E-intercept is also 100. So let's plot points, leaving a little bit of space above and below, because we're not sure how the numbers will end up being in the next one. Okay, for the next one, let's cover up E. To find the W-intercept, we're going to divide both sides by 4. So the W-intercept is 80. If you cover up W, divide both sides by 2, the E-intercept is 160. So we'll do 160 on the E-axis. We have 80 on the W-axis. All right, now we need to think about our shading. So the first line that we drew, E plus W, if that has to be greater than or equal to 100, if you plug in the test point of 0, 0, 0 greater than or equal to 100, that's false. 0 is not greater than 100. So we're going to do our little shading arrows going the opposite direction. We're not going to do them towards 0, 0 because 0, 0 is not a solution. It made the inequality false. Now let's look at the next one. If you were to plug 0, 0 in here, we get 0 less than or equal to 320. That is true, and so we're going to shade toward the test point of 0, 0. So we're going to do these arrows going down. Now the region that is shaded, it's just this little sliver, so the graph ends up looking different than it did for the tomato problem. We only have 3 vertex points. When we list them out, E will come first, so like X comma Y, we'll do E comma W. So the first 2 are easy to get, the intercepts 100, 0, and 160, 0. We have to solve the system of equations to get this one. It's the point of intersection between the 2 equations, E plus W equals 100, and 2E plus 4W equals 320. Those are the equations based on the constraint inequalities that made these 2 lines. So if we do the elimination method, I'm going to multiply everything in the top equation by -2. You could have multiplied everything by -4. And I'm going to highlight the 2 that are going to be added together so that I don't get confused. -2e plus 2e is going to cancel out. -2w plus 4w is 2w. 320 minus 200 is 120. You're going to divide both sides by 2, and we end up getting 60. 60 is the W value of the intersection point, and then if they have to add up to 100, E would have to be 40. So this represents 3 combinations that could possibly give us the minimum shipping time. All right, so I'm going to go over and recopy the objective function 5e plus 2w. And we always want to make sure that our numbers are lining up. So E is the first number listed here, and it's the first number in the equation. So we want to make sure numbers are going in the right place. We're going to do 5 times 100 books from the East Coast. We have 0 books from the West Coast. So that's a total of 500 days of shipping time. 5 times 160 plus 2 times 0. So let's think about this. 5 times 100 is 500. 5 times 60 is 300. So altogether, that's 800 shipping days. For the last combination, we have 200 plus 120. So that's going to be our minimum of 320 shipping days. All right, so we can write it out in words. 40 books from the East Coast, 60 books from the West Coast, for a minimum shipping time of 320 days.